Couple cluster theory is one of the most accurate methods you can use in quantum mechanics, electronic structure rather. Obviously full CI is going to be more accurate because that gives you the exact answer, but in practice, if you want an accurate energy or relative energy or properties, you're going to use CCSD, couple cluster with singles and doubles, and probably a perturbative treatment of triple excitations. And that's the gold standard method in quantum chemistry, CCSD parentheses T, that you probably have all at least heard of. You may not be familiar with its inner workings, but most everybody's heard of it. So I'm going to do a very top-level introduction to couple cluster theory. We're not actually going to derive whole equations because that's way too painful. But it probably is going to be a little painful for all of you guys. Okay, to review. The whole point of this lecture series is to solve, I'm going to shut this door. It's to solve the non-relativistic electronic Schrodinger equation, which you've seen many, many, many times. It looks like this. H psi is equal to E psi. H is the Hamiltonian, E is the energy for the system, and psi is the many electron wave function. This is a very difficult equation to solve, so usually we need to impose some kind of approximations to it. The first approximation is SCF, or Hartree-Fock theory, where we're going to say the wave function can be reasonably represented by just a single Slater determinant. So it's one electronic configuration. The equations are solvable. It gives you a decent answer, and it also gives you a good jumping off point for more exact methods. All the other methods in quantum chemistry are aimed at getting back what we call the correlation energy, which is the energy where electrons are explicitly see each other correlate. And that's the difference between the Hartree-Fock energy, which is not correlated, and the full CI answer would be the total correlation energy. All right, next on our hierarchy we have many-body perturbation theory, which was the subject of the last lecture. I don't know how well you remember it, but essentially we are going to partition the Hamiltonian into a zeroth order component, which we know the eigenfunctions and eigenvalues of, and a small perturbation, which is where all the in the case of Muller-Klesser perturbation theory, this is where all the correlation energy happens. And this is just the Fock matrix from SCF theory. In perturbation theory, the wave function is expanded as a Taylor series in this perturbation parameter lambda. So we say that it's equal to the zeroth order component plus the first order component plus all the way up to the kth order component. Okay? Perturbation theory is useful in understanding a lot of things about your system. It's really cheap. The MP2 scales as the fifth power of system size, which is cheaper than any of the other methods we're going to talk about next. On the complete other end of the spectrum, we have configuration interaction, which is formally exact. We express the wave function as a sum, as all possible electronic configurations, hence configuration interaction. So we start with the Hartree-Fock reference determinant, and we add in all possible singly substituted configurations, all possible, I'm putting a 1/4 so I don't double count, all possible double substitutions, JB, all the way up to and including n-tuple excitations if you had n electrons. This, what I write it as a phi, most people write it as psi, it's just easier for me to write phi. Phi IA represents a Slater determinant where I've removed an electron from orbital I and put it in orbital A. And this is just the weight of that configuration in this wave function. So it tells you how important this configuration is relative to the other wave functions, or other configurations. If I include every term in this expansion, full CI is exact within a given basis set, but it's exponentially difficult to solve, so you can only solve, say, for 12 electrons and 12 orbitals, that kind of thing. So in practice, you might want to truncate this expansion, say at the level of single and double excitations. So this gives us CISD, which is manageable, and we can solve it in polynomial time. The scaling is the 6th power system size, but this has the unfortunate property that the energy you get out is no longer size extensive, meaning it doesn't scale properly with system size. So you go to larger and larger systems, you recover less and less of the correlation energy, and it's just a very non-physical result. Okay, so we can express the wave function in a completely different way and still get a formally exact theory, and that's what we're going to do in couple cluster theory. So we're going to say our wave function is now, instead of a linear combination of determinants, we're going to define it by an exponential operator acting on the reference. So this is going to do the same kind of thing we have here, where you're going to have a combination of determinants, but you're going to have products of coefficients in front of the determinants. And this exponential form has, well, there's two nice properties about couple cluster theory. If you include every possible excitation in T, then you have full CC theory, which is formally equivalent to full CI. So you get the right answer. That's great. This exponential operator also gives us the nice property that you truncate at any order, say singles and doubles like we did for CI, and you still have a size extensive answer. So this is a really important property when you want to go to larger and larger system sizes. So the beginning of this talk, I want to look at the CI and CC wave functions in detail and see if we can figure out some of the connections between them. Anybody have any questions just about this? Okay. So I'm going to write down the CI wave function in a slightly different way using an operator instead of explicitly writing the sum. So for CI, our total wave function, we're talking about full CI and full CC right now, not any truncations. We say the full wave function is 1 plus an operator C acting on the reference. Okay? This C operator is an excitation operator. It's going to move electrons from occupied orbitals into unoccupied orbitals, and it's going to generate all possible configurations. So we can say that C is composed of a 1-electron excitation operator, a 2-electron excitation operator, all the way up to the n-electron excitation operator. And what each of these guys looks like is as follows. C1 is the sum of all occupied orbitals and virtual orbitals. The CI coefficient I showed you before, and these funny-looking creation annihilation operators, where this A sub I is an annihilation operator, is going to destroy an electron in orbital I. This A sub A dagger, the dagger means it's a creation operator, it's going to create an electron in orbital A. So when this acts on the reference function, it will, like I said, kill an electron in orbital I, create an electron in orbital A, and you end up with, so that acting on the reference will give you CIA times phi IA. Okay, does that make sense? Excitation operator. They have it everywhere. C2 is similar, but it's got, I'll go ahead and write it explicitly, I guess. 1/4 sum IJAB, CIJAB, A sub A dagger, A sub B dagger, A sub J, A sub I. So same kind of thing. Destroys an I, destroys an J, creates an B, creates an A. Okay? This is kind of a bulky notation to me, so I prefer to write them, lose the A and just write them in terms of the subscript. So I would call this A dagger, B dagger, J, I. Okay? So just like before, I'm going to write out what this wave function actually looks like. We have psi 0 plus sum IA, CIA, IIA plus 1/4 sum CIJAB, IJAB, IJAB plus 1/36 IJKABC, IJKABC times this triply excited function. And so on. Okay, CI wave function. The CC wave function, as I said before, is this exponent, oops, oh no. is this exponential operator acting on the reference. So already these look kind of similar. We can express them both as an excitation operator acting on the reference. This T is just like C. It's a sum of one particle excitation operators, two particle excitation operators, all the way up to n particle excitation operators. And it can be decomposed. Each of these pieces look exactly the same as above. I'll just show you T1 so you don't have to go crazy watching me write the same thing over and over again. A dagger I. So instead of a CI coefficient, CIA, we have what's called a CC amplitude, and we denote that with a T instead of a C. So you might ask yourself, what in the world does an exponential operator actually look like? It's actually pretty simple. You can expand the exponential operator in a power series, so you end up with 1 plus T plus 1 over 2 factorial T squared plus 1 over 3 factorial T cubed, all the way up to infinity. This is an infinite summation if we want to represent this operator exactly in a power series. That's important, that's an infinite summation. So, where can I go? If we express this in terms of T1 and T2, this ends up being 1 plus T1, T2, and so forth. You're going to have all your linear terms. And then you're also going to have quadratic terms. So you're going to have 1/2. You're going to have a T1 squared, a T2 squared, T1, T2, and T2, T1, and so forth. And then you'll have the cubic terms beyond that. And like I said, this is an infinite sum, so it's a lot of operators. If you write what the actual wave function looks like, I'm going to write it over here. We can compare it to the CI wave function in this expanded form and get some insight into what these T's mean. So we have phi equals the reference, because we just have 1 acting on the reference, plus T1 acting on the reference, so that gives us some IA, TIA, IIA, plus T2 acting on the reference, IJAB, fourth here, TIJAB. This is an important point in couple cluster theory. T2 isn't the only way to generate a doubly excited function. We also have products of T1. So this is going to be 2 single excitations that, when you act on a determinant, can give you a double excitation. So I'm going to lump that term in with T2 here. So we have plus 1/2 TIA TJB. That all acting on IIJAB. I'm only going to do this for one more, and then I'll stop. 1 over 36, sum over triple excitations, A, B, C. So here we'll have the linear term T3, IJK, A, B, C, plus we can have a product of T1 and T2. These guys commute, so I'm going to combine them with each other. We can have TIJAB, TKC, and we also have the cubed term of T1 can give us the same determinant. So we have 1/6 IJTK. I'm going to get a lot of these factors wrong today, so don't try to write a computer code based on this right here. Okay, so this gives us enough information that we can figure some things out. Let's compare like terms in the CI wave function and the CC wave function. I said that these are equivalent if you have the full, if you include the full excitation space in C hat and in T hat. So at the reference level, they're exactly the same. At the level of single excitations, we can see that CIA is equal to TIA because it's the only thing that is touching the singly excited function. For double excitations, we just have CIJAB here, but here we have this sum of TIJAB plus 1/2 TIA TJB. So number one, this gives us a relationship between the amplitudes and the CI coefficients. And number two, it implies something about the meaning of these amplitudes. I said for the CI wave function, this gives you the weight of a determinant. It's how important the determinant is. But you can't say the same thing about TIJAB because these guys are also prefactors on that determinant. So these say something that is more like the strength of the excitation process itself. So this is how important this double excitation is, and this is how important this single excitation is. And when you put all of their weights together, you get the weight of the coefficient itself. Okay? That makes sense? You guys have any questions about this? No? Okay, so obviously in the full CC limit, this is a highly nonlinear equation with a crazy operator that's infinite. So the simpler solution would be to use full CI instead of full CC because it's linear. But in practice, that's not a reasonable thing to do. So we would truncate our expansion at, say, CISD versus CCSD. And we note that the CC wave function will give us a size extensive energy. So this is the preferable way to go if we're using a truncated T operator.
What kind of Taylor series is the CI?
It's not a Taylor series, it's just a linear sum.
Just a linear sum.
Mm-hmm. Okay, so let's assume that we've truncated our operator. And let's compare the wave functions then. I'll just use operators here, so this part will hopefully go a little bit faster. Okay, so I'm going to say that we're truncating our operator, so we only have C1 and C2. And the same in T, we only have T1 and T2. So this is very weak. The wave function is plus 1 plus C1 plus C2, inside 0. So this gives us the reference, singly excited functions, doubly excited functions. The CC wave function looks completely different. You have 1 plus T1 plus T2 plus 1/2 T1 squared plus 1/2 T2. T2 plus T2 T1 plus plus T1 cubed. This comes from the cubic term. I'm losing prefactors. There should be a 1/6 here. Plus, remember it's an infinite summation. So then we could have 4 terms that are quadruple excitation. So we'd have T1 to the 4th plus T2 squared plus T1 squared T2 plus, and we go on and on. Let's say, I'll do one more. Pentuply excited functions, T2 squared T1 plus T1 cubed T2 plus forever and ever times the wave function. So we have linear terms. We have double excitations. We have very sloppy. Triply excited functions. These are all quadruply excited functions. These are all pentuply excited functions. So with this form, the full wave function actually contains contributions from every single possible determinant, because the series doesn't end until we're out of electrons. But each of those coefficients is parametrized by T1 or T2 only, not with any other higher amplitudes like you would expect in full CI when you have all those. So it seems like you have contributions to every possible determinant, which means this has got to be a really expensive and complicated method to implement. But you'll see that in practice, the way we write down the equations, we don't end up seeing these crazy higher power functions in a program you'd actually code up. Any questions?
You say that if you do the full CI, the full CC, it will give you the exact answer.
Yeah.
How dependent on the basis set is that?
It's the exact answer within a given basis set. So and that will give you an upper bound on the real energy. As you increase the basis set size, then you'll start to approach the true answer. But when I say things like exact, that means within a given basis set. Very good question.
So the T1 is the singly excited
Yeah.
single excitations, and T2 is double excitations.
Yeah.
So you have T2 by itself twice in that.
Oh, that's because where did I put it the second time?
After the 1/2 T1 squared. So it would be 1, and that T1 would be the singly excited.
Yep. And then these are
T1 squared and T2 is doubly.
That's why I thought it was missing. It was already up there, and I had it. Yep. Okay. All right, I'm going to raise this cutoff thing. Okay, so now we want to think about how we'd actually solve these equations. And again, we're going to stick to this theme of let's compare CI and CC. Normally in configuration interaction, we're going back to the full limits, not truncated. Normally in configuration interaction, you build the CI matrix and you diagonalize it, and the lowest eigenvalue gives you the ground state energy. You can also determine the ground state energy as a minimization. So you write h psi equals e psi, you express the energy in terms of that psi h psi, and you minimize the energy. And that gives you the same answer as the lowest eigenvalue. So for illustrative purposes, that's how we're going to represent the energy now. So in all cases, we have h psi equals e psi. So I'm going to left multiply by the wave function and get an expression for the energy. So if E is equal to psi, h psi, and because we're in intermediate normalization, I can't just say the wave function overlapped with itself as 1. So I need to include that here. So this is the expression for the energy. Not super complicated. If you wanted to, you could minimize the energy with respect to CI coefficients and get the ground state energy. For CI, this looks, I'll go ahead and expand it out. We have on the left the reference, the complex conjugate of our excitation operator, H 1 plus C hat reference. And downstairs we have reference 1 plus C hat dagger 1 plus C hat times the reference. Let's expand this out and see if we can actually determine all of these pieces. We have psi 0 h psi 0 plus psi 0 h, the doubly excited part. And I'm going to put a 2 in front of this because this is Hermitian, and we're also going to have the term where we have C2 dagger on the side, but it gives you the same expressions, plus 2 times the reference interacting with singly excited functions. But Brion's theorem tells us that this is 0 because single excitations don't interact directly with the reference function for an SCF wave function, for an SCF reference. What else? We got the singles interacting with themselves. The doubles interacting with themselves. 2 times the singles interacting with the doubles. Okay, that's all upstairs. What goes in the basement? I guess I'll draw a gigantic line. This is just the overlap of the wave function with itself, so it's going to look like this, the sum of the squares of the components, because each of the components is, we're using an orthonormal basis, plus the sum of IA, CIA squared. I don't need to write this out. So that sum would be contained in C1 Okay, so this is just like a normalization, and that's it. This is the reference energy. This we can evaluate with Slater's rules. This is 0. This we can evaluate with Slater's rules, Slater's rules, Slater's rules. This is just a sum of CI coefficients. We can express everything here with no problem. We could write a computer code to minimize this energy. Everybody believe me? Anybody have any questions? So this is a really strange way to solve for the lowest energy in CI, the ground state wave function. Couple cluster, starting with the same equation, is going to look similar at first, but ends up being very, very different. We have e to the t hat dagger h e to the t hat psi 0 divided by psi 0 e to the t hat dagger e to the t hat psi 0. And this is 1, and it's in my way, so I'm going to erase it. Okay, so forget the numerator. We can't even evaluate this denominator, because both of these are infinite power series. So if you wanted to evaluate this, you'd have to truncate the series somewhere. And it's kind of arbitrary where you'd say you truncate it, and you no longer are exactly representing the operator. The same is true for the numerator. It's going to have infinitely many terms. So we can't solve the couple cluster equations this way. So I hope you didn't waste your time writing all this down, because you can't solve couple cluster this way. We need to think of a different representation of the energy to solve for the CC amplitudes. And the way we're going to do that is through projective techniques. And again, I'll show you for CI, it's really simple, and then I'll show you for couple cluster where things get more complicated, which is the general story. Okay, so we start with H psi equals E psi. If you project this equation onto the reference space, when I say project, I just mean left multiply by that function. We have psi 0 H psi equals E times psi 0 psi. We're in intermediate normalization, which we did in perturbation theory, and this goes to 1. So now we have an expression for the energy. Pretty simple stuff. I'll expand this just for pedagogical reasons. So this looks like plus, it's not how I wanted to do this, but that's okay. Psi 0 H times the singly excited functions, which is 0 by Brion's theorem, plus psi 0 H C2 psi 0. So we have doubly excited functions plus psi 0 H triply excited functions, because we're talking about full CI now, not just CISD, plus higher excitations. This guy is going to end up being 0 because we have a triply excited function here and the ground state here. So these differ by 3 electrons. H is only a 2-particle operator, so you can only connect states that differ by, at most, 2 electrons. So this term goes to 0. So we have this really curious expression. Well, it's interesting. This is the reference energy. And we can express the entire correlation energy only in terms of the doubles coefficients. So that tells you that the doubles coefficients are really important. You might think that, well, why isn't CISD exact then? Because you have doubles coefficients, and you can evaluate the energy that way. The reason that CISD isn't exact is these double coefficients are influenced by higher excitations. So you need the higher excitations to relax the doubles coefficients properly to give you the proper energy back. Okay? So this equation is true for any order Ci. To get the amplitudes out, it's the same kind of game we played in perturbation theory. You want the energy, you project onto the reference space. You want an amplitude or coefficient, you project onto the space of that type of determinant. So if we want the singles coefficients, we're going to left multiply by phi IA. Full wave function. I'm not going to bother expanding this one because there's no point. On this side, we have phi IA overlap with the wave function. Can anyone guess what this value is?
That's 0, right?
No. This is going to contain a determinant that looks like that. So, because the full wave function is the reference plus all singles plus blah, 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 blah. So this guy is going to pluck out the one term that looks like it in the wave function. So this is actually equal to E times CIA. So now we have an expression to get the singles coefficients out. Same game for doubles. So this gives us a third way to solve the CI equations. We could either diagonalize the CI matrix, we could minimize the energy that I wrote before I erased it. I wanted to say last slide, but these aren't slides. Or we could do this projective technique, where we take a guess at what the coefficients are, evaluate this side, and solve for a new guess, and iterate until we converge both the energy and the amplitude coefficients. Okay, so we're going to do a very similar thing in couple cluster theory to get the CC amplitudes, except we're not going to use the normal Hamiltonian. We're going to use something called the Similarity transformed Hamiltonian. And we do this for convenience and...
Just for the last line, just raise. Can the double excitation overlap with the ground state determinant?
No, because they're different. They're different determinants.
Back to electrons.
So it can connect through the Hamiltonian,
Yeah.
but the determinants themselves are orthogonal. So that equals 0. But when we stick the Hamiltonian in there, that's our 2 electron operator that can connect the two. This is equal to IJAB by Slater's rules. Okay?
So why don't you have it in the energy?
I do have it. I just didn't write it. It's contained in here because this has a sum that contains this term.
No, I mean in the energy term.
In this term?
Yeah.
Because I got this from writing HI equals E psi, left multiply both sides by IJAB. IJAB. So this, just like in the singles case, is only going to pluck out the coefficient corresponding to that determinant. Because this is orthogonal to everything in the wave function except for that one term. Okay? Okay, so moving on, a couple clusters, a little bit different. We're going to use, it's called the Similarity transformed Hamiltonian. So we have our Schrodinger equation, H psi. I'll go ahead and write it with the exponential. Okay, this is, I just inserted the CC wave function. And we're going to left multiply the whole thing by e to the minus t. Okay? This is e to the minus something times e to the something is going to give you e to the minus t plus t, which goes to 1. So we actually have equals e times psi 0. This is what's called the similarity transformed Hamiltonian in coupled cluster theory. It's a really important thing in coupled cluster theory. So we have h bar psi naught equals e psi naught. So this looks like a new eigenvalue equation where instead of the Hamiltonian we have the similarity transformed Hamiltonian, and we only are acting on the reference function. So we're going to do the same projective techniques to get expressions for the energy and the amplitudes that we did for CI. But in this case, we're going to have psi naught h bar psi naught equals E. And for the amplitude equations, we'll have to multiply by, everybody see? I multiplied this guy by psi naught, so I get a 1 because they're the same and it's an orthonormal basis. So this is E times the singly excited function times the reference. This goes to 0 because they're orthonormal. So we have 0. We get ijab h bar psi naught equals 0. So now we have an equation for the energy, a nonlinear equation because we have exponentials everywhere for the singles amplitudes, and then this is done all the way up to n-tuply excited functions. The equation for the doubles all the way up to n-tuples. Unlike the CI case, we've decoupled the amplitude equations from the energy. But other than that, these look very similar to the CI equations, until you remember that this isn't the normal Hamiltonian, it's the similarity transformed one. So the question now becomes, well, there's a couple of things that we need to think about. In the great scheme of things, this is no longer a Hermitian operator. And quantum mechanics tells us that a physical measurable like the energy should be the expectation value of a Hermitian operator. So is what we just did really legitimate for doing high accuracy quantum chemistry? I can tell you that it is on paper, because when you don't truncate T, this operator has the same exact eigenspectrum as the normal Hamiltonian. So you should have the same eigenvalues. That's not necessarily true when you truncate the operator. So by introducing size extensivity into our method, we've sacrificed the variational nature of it. So if we truncate T, we're not guaranteed that the energy we get out is going to be an upper bound to the full CI solution. In general, it's pretty close to the variational, what you would get if you did this variationally. But it's just something you need to think about, and it has implications for things like determining excited states and determining properties, because our Hamiltonian isn't Hermitian anymore. Okay, any questions here? Okay, so now we get to figure out how in the world do we express these equations that involve h bar instead of h. Because the CI equations where we just had h were very simple. We just follow Slater's rules to evaluate all the matrix elements. Okay, so we're going to use the Campbell-Baker-Hausdorff CBH expression for the similarity transformed Hamiltonian. This is an exact expression, again with an infinite sum. We say that this is equal to h plus a whole bunch of nested commutators. You guys know what a commutator is? Commutator of a with b is equal to ab minus ba. And if this is equal to 0, you say that these operators commute. And if this is equal to a number, then they don't commute. And that's the value of the commutator. Okay, so we're going to have a whole bunch of nested commutators. We start with h commuting with t plus 1/2 double commutator h with t with T plus triple commutator okay, and I'll only write one more. And the quadruple guy. 1, 2, 3, 4. Am I going to have space? Just barely. Plus infinitely more terms. So it really looks like we screwed things up horrendously by introducing this similarity transform Hamiltonian. This is way more complicated than the linear Hamiltonian we use. Just this guy in CI theory. But we can use the properties of these operators to simplify this expression. So for the next little bit, we're going to talk about how to express a quantum mechanical operator in what's called second quantization. And we're going to talk about the properties of the second quantized operators to see if we can simplify them. Okay, we're going to talk, these are those creation annihilation operators I mentioned before. So we have AP dagger, which I'm going to write as P dagger, is creation. AP, which I'm going to write as P, is annihilation, which I think that's how you spell annihilation. And they have a few basic properties. Let's see. So say we had a function that had orbital p occupied. We act on it with the annihilator. We're going to get the vacuum state. So we now have no electrons. Our wave function our determinant has no electrons in it. If we tried to act on the vacuum state with an annihilator, we'd get 0 because there's nothing to annihilate. Similarly, if we acted on a state with Q occupied, but with the P operator, this gives us 0 as well. The creation ones are just as simple. P creator acting on the vacuum gives us P. Let's say P creator acting on this guy. It's going to give us 0 because P is already occupied, so you can't put another electron there. This is tedious, I know, but we need to go through this. These guys obey anti-commutation relations. So the anti-commutator, as opposed to the commutator, is PQ plus QP instead of minus. That's all that anti-commutator means. So let's do PQ first, since I already wrote it up here. This commutator is equal to 0. I'm just defining this, so you'll have to believe me. P dagger Q dagger is P dagger Q dagger plus Q dagger P dagger. This commutator is also 0. This implies that PQ equals negative QP. So if you want to swap them, you just get a minus sign. This implies P dagger Q dagger equals negative Q dagger P dagger. Again, swapping the operators, you'd get a minus sign. One more, let's see. We can do P dagger Q, where we have one creation, one annihilation. So this is P dagger Q plus Q P dagger. And this is the only one that doesn't equal 0. This is a delta function. It gives you 0 when P and Q are different, and it gives you 1 when they're the same. So armed with these crazy things, we can represent T hat and H in terms of these types of operators, and we can use these anti-commutation relations to derive programmable expressions for a couple cluster theory, or CI theory if you want to do things this way. So in second quantized notation, the Hamiltonian has a 1 electron piece, HPQ, times P dagger Q, and it has a 2 electron piece, PQRS. This is the 2 electron integrals that you guys love so much, times P dagger Q dagger SR. Okay, any questions there? Okay, so now And we already know that T, say, for example, T1 is the sum IA of T, IA, A dagger, I. So what we want to do is figure out what these commutators look like and see if we can infer any interesting properties about them that can help us simplify this. I want to point out here that in this whole talk, when I use I, that means occupied. IJK is an occupied orbital. ABC is a virtual or unoccupied orbital in the reference function. And PQ and R and S are general indices. They can be anything. So, okay, so let's look at the commutator. Let's simplify everything and just look at the commutator of T1 with the one electron part of the Hamiltonian. Okay. Commutator. We have H commutator with T, so we'll put the one electron part PQ over here, and we'll put the one electron excitation operator AI here. This is just PQ AI minus AI PQ. And now this is where the real fun begins. We're going to split everything up based on these rules. So to get a useful expression, what we want to do is put this in what's called normal order, which just means we want to move all of the daggers to the left and all of the ones without daggers to the right. So the first one we want to move is this guy. So we say that this term is P dagger times what's QA equal to? So that's like this. This would be the delta minus the other piece. So you have delta QA minus A dagger Q times I. We can also break this one up. A dagger is delta IP minus P dagger I times Q. Any questions? So this gives us a few terms. We have delta QA P dagger I. Dagger is to the left of the not dagger, so this is in the right order, plus, no, minus P dagger A dagger Q I. All the daggers are to the left. That's great. From this term, we get Q delta Q I P A dagger Q. All the creation guys are on the left. That's great. Minus A dagger P dagger IQ. Can anyone guess how this is related to this one? Actually, I have a plus here and a minus here. Okay, what is the commutator between Q and P when they both have a dagger on them?
Negative.
Yeah. So we could say that this term is negative P dagger, Q dagger. Oh, shoot. What did I do? This is an A. Okay. This is negative P dagger, A dagger, I, Q. Do the same trick here. It's actually plus P dagger, A dagger, Q, I. So our whole expression has 4 terms, and these two are identical to each other and of opposite sign, so they cancel out. What is the point of this entire exercise? We did this commutator, and we ended up with the only functions that survived reduced the number of general index operators by 1. So we had an expression with PQIA minus AIPQ that had 2 general index operators, P and Q, in each term. And now we have a term with 1 P and a term with 1 Q. In general, this is true for all of these commutators here. The Hamiltonian has at most 4 general index terms. So we can say with absolute certainty that this series truncates after the 4th nested commutator. So while we got to cut off everything that I didn't write, we're still stuck with all this other disgusting nonsense. And this is just a property of the Hamiltonian, and the fact that these T1s, the T's commute with each other. It's a very important property. And that gets mucked up when you go to multi-reference coupled cluster theory. Your T's may not commute with each other, and you don't have this beautiful truncation of this series. Okay. DJ. Okay. So now, armed with this knowledge, how in the world do we derive the coupled cluster equations? We know that the similarity transform Hamiltonian truncates after the fourth commutator. We had equations for the energy and the amplitudes before, and now we just need to plug things in and do a lot of plugging and chugging that I'm not going to make you guys sit through. You're very, very welcome.
Thank you, Eugene.
Yeah. Okay, so back to our equations. We had 0. We had the CC energy equal to, I'll just leave that at CC, at E, equal to this. And we had equations for the amplitudes, CIA, I'll write as H bar again, equation for the doubles. Oh, I should point out that CBH theorem is true even when you truncate T. So unlike the properties that we lost before when we truncated T, the variational nature, that series naturally truncates after the fourth commutator, regardless of the form of T. Okay, so now we're gonna ditch full CC and we're gonna think about CISD. So I'm not writing any more equations. And we need to evaluate all these matrix elements using the rules of normal order operators that we had before. So I'm going to go through a very simple example to show you how this is done, and then I'm going to just give you the result. But we got to work through this one example first. So say you want the value of a matrix element between two determinants. And let's say the operator we're interested in is, we're going to call it A, and it's got some general index terms, just like the Hamiltonian. And I'm going to say that A is equal to PQRS, with daggers on Q and S. We play our commutator game again. So this is delta P, Q minus Q, P times. I'll go ahead and expand this one at the same time, or is that too complicated? Whatever, we'll figure it out. Minus S dagger R. So this gives us one term that's delta PQ delta RS minus delta PQ S dagger R minus Q dagger P delta RS plus Q dagger P S dagger R. This guy is the only one of these that isn't in normal order yet. So we need to expand this one. We have Q dagger times delta PS minus S dagger P times R. So this gives us delta PS Q dagger R minus Q dagger S dagger P R. Okay, how in the world does this help us? It doesn't yet. Say we wanted to evaluate the expectation value of this operator with the vacuum state, the state with no electrons. So we have no electrons in our bra, we have our operator in the middle, we have no electrons over here. Let's expand out the normal ordered form that we just derived. PQ delta RS. I'm only going to write one of the terms, minus delta PQ S dagger R plus the other terms. What happens when I act on the vacuum state with an annihilator? 0. So the only term that survived was the term that had no creation or annihilation operators left in it. So we know the expectation value of this operator with the vacuum state is just delta PQ delta RS. Pretty cool. That fell out really easily. The problem is we're not interested in vacuum states in any kind of electronic structure theory. So we need to think about what if we had a state with orbital I occupied times A hat times orbital J. Well, we just play the same kind of game. We pull out these electrons in terms of creation or annihilation operators. So we have vacuum. I know this looks like an annihilator, but when it acts to the left, it acts like a creation operator because it's the complex conjugate. So we have I times A times J dagger times vacuum. And so this is our new operator, I, P, Q dagger, R, S dagger. So we do the exact same game, but now we have this guy with 6 creation annihilation operators. And we'll get out some crazy sum, and we're going to retain only the ones with no creation or annihilation operators. These are called completely contracted terms. So in general, you could write down any determinant and figure out what its non-zero elements of its expectation value are in this sort of way.
I didn't know missing J dagger.
Oh, you guys are so smart. Okay. Does that make sense? You can imagine this is a horrible idea to try to do this for the couple cluster equations. So I'll just tell you there's a theorem called Wick's theorem that makes these rules a lot simpler. That you can derive the non-zero terms lickety-split. It's still really complicated and really prone to errors. And then you need to generalize Wick's theorem to make things more simple by having a form of it where you have, rather than the vacuum state, you have the reference over here, which is what we're actually interested in couple cluster theory. So I'm not going to derive any of that because that would be, I have notes on it if you want to see them. I don't think that you do. So anyway, that's the basic idea. You use Wick's theorem or commutator-anti-commutator relations to derive these expressions in couple cluster theory. And then you just program them up. Easy as that. So we're going to assume that someone else worked out our equations for us. And I'm just going to write one of them down for you. You play the game with creation annihilation operators for Wick's theorem, and you get a very simple expression for the energy. The couple cluster energy, when you include single and double excitations, is going to be sum of I, J, A, B. I think there's a fourth. Wait a second. Where did my energy go? Ij, AB times T, Ij, AB. Now I can tell you, you would fill up 3 pages of awful algebra if you derived this equation using Wick's theorem. But it's really simple. Oh, that's actually not it. There's a... And full disclosure, I probably have 1/2 and things like that completely wrong here. But the point is, you have your doubles amplitudes and your singles amplitudes pushed against this 2-electron integral. That's your expression for the energy. So just like in the CI case, where the energy only depended on the doubles amplitudes, it's similar here, but you have a product of singles also contributing to that. The equations for the CC amplitudes are far more complicated, so I wrote them down ahead of time, so I wouldn't have to here. So we have, for the T1 amplitudes, we have T1 itself times some orbital eigenvalues, plus terms with the Fock matrix, with singles, Fock matrix with more singles, we got some double amplitudes in the Fock matrix, a whole bunch of 2-electron integrals, doubles amplitudes, singles amplitudes, crazy products of things. We have a product of 3 singles amplitudes here. It's complicated. For the doubles equations, same kind of idea. We have these orbital energies times doubles amplitude equals just a 2-electron integral plus the same kind of crap that's in the singles equation. These look really, really complicated, and at first glance, well, they are really, really complicated. That's why they look that way. And at first glance, you might think that these equations scale as the 8th power of system size, because we have ijab, so there are O squared, O being occupied space, V squared of these guys, sort of O squared, V squared equations. And these equations have terms that scale as the 4th power of system size in them, O squared, V squared. So naively, you'd think this scales as the 8th power, O to the 4th, V to the 4th. But you can factorize terms and make intermediates and be clever, and you can get the scaling back down to the 6th power of system size, just like CISD. So incredibly complicated method, but not that much more expensive than CISD. In fact, the most expensive term is this one, and it occurs in, well, at least the linear part of it occurs in CISD. I want to see, couple cluster theory is very closely related to perturbation theory. So one of the last points I want to make is how close are they at the MP2 level? Oh, you solve these, before I get to that, you solve these by taking a guess at t, evaluating the right-hand side, and updating t again. Over and over until your energy stops changing and your amplitude stops changing. So what happens if we take a guess of t equals 0? So in our first or 0th iteration, we have a guess of t equals 0. I'll go ahead and tell you if we have an SCF reference, this whole term is going to be 0 after the first iteration, so I'm not even going to worry about it. So let's see, TIA is 0, and then every one of these guys has a t in it, so they're all going to be 0. The only term that's going to survive is ABIJ. So we have TIJAB after one sweep through this is equal to ABIJ. I'm just going to divide by the orbital eigenvalues here. Anybody recognize this expression?
MP2.
This is the MP2 form of the first order doubles amplitudes. So if you run any coupled cluster code, as a byproduct, it's going to print out the MP2 energy for you. And that's because in the 0th iteration, you end up with the MP2 wave function. Some codes will also spit out higher order terms in perturbation theory as well, because everything here is related to perturbation theory somehow. The linear terms are related to the MP3 energy. The quadratic terms contribute to the 2nd order wave function, that kind of stuff. So let's look at the energy just to really convince you that this is the same as MP2. We have EE is some IJAB times it's the same as the MP2 energy. How about that? I think. Yeah, so one last point. I said this contains higher order terms in perturbation theory. Coupled cluster with singles and doubles excitations is complete through 3rd order perturbation theory, and it's partially complete through 4th order. It's complete in the space of singles, doubles, and quadruples, but it's missing some connected triples terms. We have the disconnected triple excitations, where you have T1 times T2, that kind of thing, but you're missing contributions from full T3, and you need that for 4th order perturbation theory. That comes in at parentheses, CCSD parentheses T. There's an expression for the triples contribution to the energy. It's kind of a cheat to get a CCSD full T-like answer in just one non-iterative sweep. And that method is complete through 4th order, full 4th order in perturbation theory. And has a lot of pieces to 5th order, and this guy has pieces to infinite order. Coupled clusters related to a lot of other methods. Closely related to CI, if you take out all the linear terms and add in an energy leave only linear terms, add in an energy dependent term, you can get out CISD from this. If you just take the linear terms and don't add that extra term, you get what's called linear coupled cluster. If you take out the 3rd order and 4th order terms, here you get something called quadratic configuration interaction. They're all really closely related methods. That's it. So if you have all this at your disposal, you can make a lot of simpler methods out of it, which is nice. Okay.